Hello and welcome to the fourth lecture of Machine Learning for Robotics and Computer Vision. In this lecture we will talk about ensemble models, which will enable us to learn stronger combinations of different classifiers, which allow us then in the end to more robustly classify also data sets which are more complicated. But first let's look at what we did last time. So in the last lecture we talked about classification models, and specifically about discriminative models, but also some generative models. So we talked about naive Bayes, which was an example of a generative model, but also about decision trees and logistic regression and softmax regression, which were discriminative models. And specifically, the decision trees will now play a role, so you will now figure out why we discussed this in the end. But we talked also a little bit about gradient descent. And gradient descent is the main method that is mainly used in machine learning to learn models. And this will be a reoccurring pattern which we will use in the end. So we derive a gradient of a method and then use this gradient to optimize the model. And but now let's start with the next lecture. So what is about the classification with ensemble models? So here the main idea is that we want to use something like the wisdom of the crowd. So that means we have many maybe classifiers that are maybe not as accurate for the specific example, but when we combine them, then maybe many of them vote for the correct answer. So this is something that you can also maybe observe when you have many people, and maybe not all of the people have maybe the right idea, but when you combine many votes from many people, then you will find maybe in the end the right answer. And here we want to combine so-called weak learners, something like a decision tree, which is not grown very deep, but which gives us something like, weak means here that it's maybe a little bit better than random guess. And we want to combine these weak learners, so each very inaccurate for itself, but by combining them, we are getting out a stronger model in the end. And as I said, each individual weak learner is maybe inaccurate, so it will not always return the right prediction in the end. But the vote that it gives then maybe for some specific data point can then be aggregated from multiple weak learners such that it gives then the right prediction out in the end. And the simplest possible ensemble is just by using some weak learners and just combining them via a weighted sum. So here these PJs are the weak learners, and by combining them in a specific way, here maybe by alpha j's, then we get a strong classification model out in the end. And in this lecture, we will talk about different methods how to get these weighted sum out in the end, and maybe do it just a little bit clever, but just by using the alpha j, just the weighted mean of the classification models, but do it in a little bit smarter way in the end. But first, we start with a very simple approach to learn such an ensemble. So the main deal is here, how do we get maybe a model which we want to learn to give out different predictions for some data set? And the first thing that was invented was basically the Bayesian approach. So Bayesian stands for bootstrap aggregation or aggregating, and here the idea is very simple. So we take an input data set, something like this. So this is a little bit more complicated than our linearly separable data sets that we had before. So you see that some red points are also here, and so you can guess that there may be something like a logistic regression will not do very well in the end. But the idea here now is with Bayesian that we just determine new data sets by sampling. So we are sampling from this data set here points, in this case with replacement, so that means we are also sampling points multiple times. But the idea is that we get new data sets out of this. So, and as you can see, these data sets are a little bit different. So here we have some more red points than here. Here's some red point here, but the red point is missing here, so this training example. And so we have really different data sets. And the idea is now to train classifiers on these different data sets We can use whatever we want. We can use the decision trees, but also logistic regression in this case, and then combining this into a stronger model. So when we do this, for instance, with the logistic regression, we get now something like this. As you can see, as the data sets are different, for instance, here this red point leads to pushing the decision boundary in this way, which we not have in the other cases. So, and this leads really to different logistic regression models in this case. And when we learned this 3 different regression models, then we aggregate this by just the sum over the models, where we divide the sum by the number of the models that we trained. And as you can see, the prediction here is now, where all models agree, we basically get a very high probability for this certain class. And where the models don't agree, we get some less confident predictions. And this is something also that we want to have in the end. So we want to know basically that we are a little bit more uncertain in these areas. And this leads then also maybe to an approach that generalizes better to the situations that we are encountering then in the test set, so to say. And but this Bayesian approach is maybe not the right way to do, and there are certain reasons why this maybe not works always. So there are certain problems with the Bayesian approach. So we get correlated weak learners when the sample subsets are too similar. So that means in this case that we discussed before, there were only some very few training examples, but when you can imagine when you have many more training examples, then each of the sample subsets is maybe not so different from each other. So that means that the classifiers that we learn from this, so the weak learners, are not very different from each other. So that means that the predictions that they make will be also not that different. And when we then combine them, then they will not turn out to be maybe very different from what we got in the beginning with the weak learners. So this is one problem. Another problem is that we can only use weak learners which are somehow unstable. That means if something changes in the training data, then this will also change somehow the classifier in the end, or the weak learner. So that means when we have a very robust classifier, then sampling will not change so much, because maybe it's robust to multiple points at the same in the same region or something like this. So therefore we need somehow some unstable model. So and with this we then get different predictions. And one thing that we also don't like always is like that it reduces basically the number of training examples. And this is maybe also a problem. So, but the thing is, we can maybe use the idea from Bayesian, but make it a little bit more powerful. And in this way, there was a method invented, which is also quite often used, and this is the so-called random forest. And as I promised in the beginning, so decision trees will play now a more important role in this part of the lecture. So, and here the idea is quite simple. So the thing is here that we train T different decision trees, and decision trees are not very deep. So here in this case they have only depth 2, but we use many of them. And to introduce some more randomness in the learning of the decision trees, so because as I said, when we have larger data sets and we do the sampling with the Bayesian, maybe the data sets are not so different. So what we do, so the simple idea is here that for each of the decision trees we are not only randomizing the training data that we put in, but that we also randomize the features. So that means we select only a subset of possible splits, and by using only a subset we get very different decision trees in the end, as maybe shown here with the different class distributions in the leaves. And in the beginning, or most often when you have random forest, then there's also Bayesian involved. So we generate bagging, but also have the randomization via the different split functions. And as I said, the randomization of the split function reduces in the end the correlation between the weak learners. So by using very different split functions for all the decision trees, we get then very uncorrelated models in the end. And the appealing part of the random forest is in the end that the inference is very simple. So because we just have to run each example through the decision trees, so each of the decision trees will then maybe end in a different leaf node, because every tree has different split functions. And then the output is just again the average overall predictions. So you take basically the predictions from each leaf and then do the average over everything. So this is the same as in the bagging approach. And one question that arises, how do we get the random trees, the decision trees, to do something more randomness? And for this, one method would be, for instance, to introduce this randomness in the creation of the nodes. So here we have the same method as before. So we, for creating a node, we have this recursive method that creates node from the beginning, splits the data sets. When it reaches a leaf, so when we have reached the maximum depth, then we create just a leaf from the set that we give in. And for the inner nodes, we just use the splits as before. And to introduce the randomness, we are now using here some random number generator to generate random selection of features. So we select for each feature the dimension that we want to split. So we have again the same splits as before, so the thresholding, which is very simple to do. And then we select just the dimension randomly. Then we split it with the function, and then we determine again the information gain. And when the information gain of this split is higher, then we just keep this split function here, and then we do the random sampling again. So and as you can see, when you just maybe use rho equals to 1, then you make only one decision. And as long as the random number generator is not always the same, so there's different seeds for each decision tree, it will lead to a lot of randomness in the end. So with this parameter, you can basically steer how random the decision trees are in the end. So very simple fix to get the random trees, the decision trees more random in the end. And when we think of the random forest, we have here the main hyperparameters are the number of the trees, of course, the maximum depth of the trees, and of course the randomness in the end. And now I want to give a little bit insight what the different parameters maybe lead to in the end. And for this, I'm referring always to the report from Creminici. And here the pictures are taken from this technical report. And for the number of trees, we can clearly see when we increase the number of trees, we get more smoother regions in the end. So, and this is something that we also want to have in the end for the predictions. So that means that we don't make the hard decisions between whatever it is one class and the other class, but have this uncertainty in between. Because this is this thing that we also want to have in the end from the prediction. That it tells us that when you are somewhere here, you should be also very uncertain. And this is of course achieved because each tree does a little bit a different split in the end. Here in this case, the splits are just randomly choose, not because of some feature, but somewhere in between. And therefore you get for each tree a different voting. And when you then aggregate all these votes from these trees, then in this region, the trees will not agree very much, and therefore the probability from the posterior that you get in the end is something around here 0.5. And the more you go in this region where you have basically training examples and where the decision trees maybe will turn also to give the same prediction in the end, the higher the confidence there. And this is the influence of the number of trees. So usually you want to use many trees in the end to get such a nice posterior in the end. When we talk now about the depth, then we have to choose there basically a depth that's somehow right in the end. Because if we choose the depth too small, then the individual trees, so here we always use the same number of trees in the end, but we only vary the depth of the trees. And as you can see, when you use only a depth of 3, then you might get here some regions where you see that points here, these yellow points, are not correctly classified, and yeah, here some points from this yellow part are also not correctly classified, and a lot of the red points are also wrongly classified. And because the decision trees are not powerful enough basically to figure out that there's something happening. When you then maybe use something like depth 6, we get some more reasonable result in the end, where also the points that are here are correctly classified, and here the points are also getting the correct class assignment in the end. But when you grow the trees too deep, then you will also see that it maybe fits too well. So as I said in the regression lecture, which also come up with the classification lecture, where we had the logistic regression and we train it too long, then we will get overconfident results here in the end. So, and in these regions, maybe we see then there are some overfitting. So it's getting just too perfect in the end. And so the depth of the trees steers somehow how well the trees fit the data in the end. So, and yeah, there's some tweaking possible. So also it's not always that depth 6 is maybe the right answer, but it's maybe also another depth. So therefore, the thing that we discussed in the first lecture, so you have your validation set, and then you choose basically the parameters that just do the right thing for the validation set at the end. And talking about the randomness, here we also see that we have to basically use a large randomness to get nice boundaries in the end. Because when the randomness is too small, then, as I said, all trees basically agree on their prediction in the end, and then we get here not the uncertainties in the end correctly. And therefore, when we use a larger randomness, we decorrelate the trees, and therefore overall reduce the agreement between the different trees. So here you see that the decision boundaries are, or the posterior is basically much smoother in the end. And therefore we get also the smoother boundaries here. So, but as I said, so there is no specific setting of the hyperparameters, but it's something that you have to tune in the end. But luckily, there are not so many parameters in this model which you have to tune. So number of trees is maybe something that you can easily tune because you always want to use many trees in the end. The depth of the trees is maybe the second important parameter. And I would say for the randomness, you always want to have some large randomness in the end. When we talk about random forests, they were quite popular also in the computer vision community some time ago. But there they were just called decision forests. So when you look at papers and they will tell you where we use the decision forest, then it's basically a random forest. But one specific point that also, as I said in this technical report from Cremonesi, which is an excellent resource to also have different discussion for different topics like regression, also density estimation or something like this. This is also all covered in this technical report. But as I said, so in this decision forest, so they advocate the view that we don't do bagging at all, so but just use the random splits in the end. And the advantage is that then all the trees see always all training examples, which is maybe something that you want to have in the end. But just as a note that maybe when you see these terms and you maybe think like, oh, is this something new? But It's just this similar to the random forest. As I said, when you want to know more about decision forests and what you can do with decision forests, and also maybe some application of the decision forest in the computer vision domain, then look at the technical report. When we talk about random forests, then we see that there are certain advantages. So the one advantage is that because the training of each tree is basically independent from each other, we can just use whatever, as many cores or many computers as we want to train them. So we can really speed it up. So we don't have to train each tree after each other, but can train it concurrently. And another feature of the decision forest, or the specific thing that we use with the randomness, that we only have to evaluate specific splits, is that we can also use maybe more complicated split functions or more complicated features that we only need to compute when we really want to decide which split is maybe optimal in the end. And what is also one insight from many papers that use decision forests in some way is that they are working quite good or quite well. So they are a good off-the-shelf method that you can just apply to your methods. And of course, because you're using decision trees, this is also very simple to implement in the end. And as I said, the hyperparameters, there is a certain set of good hyperparameters, but it's not so critical to get them very specifically right. So that means as long as you are in a certain range, then you are fine, and then you can do very well with the random forest. It's not like whatever that when you change from 200 to 201 trees, that you will get a very different result in the end. So you don't have such high variance in the output in the end. But when we talk about advantages, then of course, then we have also some limitations. So the bagging in the random forest use just the same weight for all V classifiers, because they treat basically also the weak learners basically independently. And therefore, you cannot exploit somehow the results of one weak learner for the other weak learner, or maybe correct in the end the classification results from one weak learner to another. So, and therefore also the individual models are very independent, which is an advantage. You can train them very concurrently, so you can use as many cores as you want because you don't depend on the other model. But might be also a limitation because you cannot use basically the wrong predictions or the correct predictions from before to correct them in the end. And this is something that we might want to do. And for doing this, some other method was invented, and this is the so-called boosting. So in boosting, the general idea is to find weak learners in a stage-wise manner. So that means we learn first a weak learner, then use the results of the weak learners to improve the ensemble in the end. So we basically boost the performance. So therefore the name boosting makes somehow sense. And in boosting, we want to optimize the weak learner in ensemble such that training error is reduced. So that means we first learn one weak learner, and then based on this, we want to learn specifically one weak learner that reduces the training error in the end. So the longer you train, so the more stages you have in your training, the lower the training error gets in the end. And one specific assumption is here that the weak learner must be so strong in the end. So as we saw in the random forest, you basically need to use some depth of the decision trees in the end. So that means the weak learner there is not so weak in the end. And in the boosting, the cool thing is that there the weak learner must only be better as random guess. A little bit better is just enough. So you can really use, or whatever, not so deep trees, or very simple weak learners in the end, and still get a good result out of it in the end. So, but to discuss boosting, we have also to go a little bit back in history, and the first famous boosting method that was invented was basically invented for binary classification. And here the functional view of classification was very prominent at that time. So that means the classifier, instead of returning a probability distribution over different classes, just returned the label -1 for the negative class and 1 for the positive class. So before we had just 0 and 1 for the classes, and here we will have -1 and 1. So keep this in mind. And another thing is that we now have the strong classifier, which is capital H, is a linear combination of the weak classifiers, lower h here in this case. And I denoted them by I because there are many of them put in the ensemble, and the weights of the classifier is always with the same index. And to get the classification result that we want to have in the end, so the -1 and 1, we are just using the sign function here on the result. So that means this sum maybe returns some number, whatever, 10 or -10, but we are just using the sign in the end from this. So that means here the sign function is just returning -1 if the argument, so the part inside the brackets, is negative, and 1 when it's positive, or 0 in the end. And this is something that is now used in the end. So the first prominent method to do boosting was the so-called AdaBoosting, or the AdaBoost, which stands for adaptive boosting. It was specifically invented for binary classification, and the idea that is behind AdaBoost is that we can get a model or weak learner that basically leverages the knowledge that the other weak learners had before by using weighting. So we have weighted samples in each stage, and we weight it in a specific case, in a specific manner, such that the weak learner can exploit this in the end. And as I said, so the general idea is that in each stage the ensemble, so the whole capital H, by adding these small h's, is getting better. And the AdaBoost algorithm is not so complicated. So as I said, we have now not only our training example xi, so a training vector here in this case, yi for the labels, but we also have a weight. And then in the beginning we just, we have n training examples, we just initialize the weights by 1 over n. And then we iterate in a stage-wise manner. So we are starting with m equals 1, and we do this for capital M times. And then, as I said, in the end, we just return the decision function in the end that tells us the sign of the sum of the weak classifiers is then our classification result in the end. So -1 and 1. And now to move further, so that's now the magic part, so to say. So how do we do the iteration? So we train the weak classifier with the weighted examples. So the thing is that the weak classifier has somehow to account for the weighting in the end. Otherwise, this whole method makes no sense when it doesn't care about the weighting. But we now assume that the weak classifier somehow uses this to some extent. Then the next step is, when we trained this weak classifier, we determine the error of the weak classifier. And this is then the weighted error. So that means we just sum up over all examples and look if the weak classifier did the right decision. So if the label is not correct, then we just accumulate the weight of this training example here. So this is then the estimate of the error in the end, but the weighted error, that's important. Then we determine the weight that we are using also later. And this is just the logarithm of 1 minus this error rate divided by divided by the error rate. And this comes from the derivation in the end. So, and the weight is now updated as follows. So this is somehow the magic part. The weight is just then the exponential of this step that we determined, and then we are just taking also only in account the examples, the points that were wrongly classified. So that means when it's correctly classified, this term will be 0. So the exponential of 0 is then of course 1, and so the weight of the correctly classified examples will not change in this round. And one thing that you can now do is to renormalize the weights in the end. So in the end, the weights are always between 1 and 0 and 1. But for some examples, they are getting much larger, and for some examples which were correctly classified, they are just staying the same. And yeah, you do this now for m rounds, and then you get out the ensemble in the end. And as I promised, so the decision trees will also play now here a role. So we're also quite often used here for AdaBoosting, but in the end you can also use some other weak learner for this. So something like a logistic regression, which accounts then for the weights. Now we have to do the decision trees such that they account for the weighted samples. And for this, as you remember, we had the information gain, and we have now to derive, or we have to use a weighted information gain. So in the classification lecture, we defined the information gain as the entropy minus the sum over the SL divided by S, so the number of elements in one set divided by the number of over all things. So basically we just assumed that all the examples were just weighted with 1. And here we are counting exactly for the weights. So that means we sum over the weights in the subset and divide it by the weights over all examples. So S is always the union of SL and SR, as you might remember from the from the classification lecture. And what we also now have to do is we have also to account in the entropy for this term, or for the weights. And for this we are just using the same idea. Basically we are not now counting over all the examples in the end, but we are just using the weights for each example and divided then in the end by the sum over all examples. So, and when we use this, then we get information gain which accounts basically for the weighting of the examples. So that means when we now look in, I will show in a bit an example, then you will see that decision boundaries changes because of the weighting. So these are the important parts here. And for the leaves, we have also to account for the weights. So at least I account now for them. So that means if the training examples are splitted and then reach some when leave, then we are just saying, okay, when the weights of the examples that had label -1 are larger than the sum over the weights for the examples that are 1. So basically, yeah, what decision we will do then is basically we say, okay, if the weights from the -1 examples is larger, or the sum over the weights of -1 is larger than the sum over the weights for 1, then we just return 1, and otherwise -1, and then otherwise we return 1. So this accounts then for the weights in the sets. And when we use this, we can then do some example here. So here we have a little bit more complicated example where we have on the left, I always show the posterior of the ensemble and its state. So that means the colors that you see in the background are basically the posterior of the ensemble in the end. And what you will see also here is the decision boundary of a decision tree. And here in this case, I'm just using a very simple decision tree with just a single split node. So that means it just does one split and then decides on the classification in the end. And in the beginning you see, so the size of the boxes will change, or the size of the points. So, and in the beginning all the examples is just have the same size, so that means they have equal weight. And on the right side, you will see the error. So it's just the unweighted error in the end. So to make it comparable in the end. So that means we just count how many examples we have right, or wrong in this case, and divide it by the overall number of examples. So therefore it ranges from 0 to 1. And we want to have in the end a training error of 0, or near 0 in the end. And when we do the first round, we are just learning the decision tree and the optimal split that it finds out. So it goes over all examples in this case. So there's no randomization here. So it's just checking all the splits. And then with this, it finds out that this is from the information gain perspective, from the weighted information gain perspective, the best split. So it splits just here the examples like this. And when you remember the algorithm, it now looks at which example it gets wrong, and based on this, it then reweights the examples. So that means with this split function here, so this corresponds also to the posterior of the ensemble, these blue points are wrongly classified. And here this, maybe this red point is also wrongly classified, but also these blue points. So that means from the weighting perspective, the weight increases for these points, as shown here. So these examples are all correctly classified, and for this it's increasing. And then because of the renormalization, the overall weight of these points are decreasing in the end. And then we have the reweighted examples, and then we can go over to the second stage of the training. And with this, we are then using, we are learning a decision tree again. So here you saw the split was before like here, and now the split function is here. So because now we have the influence of the blue points, and it tries now to get the blue points also right. And therefore it changes the split up. So and as you can see here, as the split changes and the ensemble basically also changes, the error rate is going even a little bit up, because now it gets the blue points right, but the red points are wrong in the end. So, and therefore there are a little bit more red points here in this case than blue points, so therefore the error rate goes a little bit up. So that means now the ensemble is basically a little bit worse than before, but maybe that's still right when you take into account all the points in the end, then maybe it does still the right thing in the end. So, so this is not the last round. So as you saw, now not only these points and these points are get the high weight, but these points also get a higher weight, because now these are wrongly classified in the end. So that means this part and this part is not so important anymore. So in the second stage of the training, it now found out that these are the points that it really should take care about. And instead of now doing the splits in this direction, as you will see now, it now does the splits in the other direction, because then suddenly the information gain will turn out that doing splits in this direction is not so helpful. And therefore doing now the split in this direction will help much more to get the right result in the end. And as you can see with this split at this specific point, because of the reweighting, we then also see the behavior that we want in the end, so that the training error is reduced. And as you can see also here, because we have now the ensemble of the different models, they will then also turn out to be that these blue points are now correctly classified in the end. And with the split, you see here the split, these points are all correctly classified. Here these points are not correctly classified. As you can see now, the weight is decreasing for these points, but increasing for these points. So the ensemble has in the end, wants to get maybe these points correctly then in the end. So, and when we do this further, then you see, because now the weighting changes from here to here, so the best split that it can find then is then on the other side to get this also then correct. And as you can see, now these points are not correctly classified anymore. And and therefore the weight of these points should increase again. So as you can see here, these weights are now smaller, and now this is the important part. As you can see, over time and using the weighting, it can figure out where to go with the next splits. And using this, we can then iterate furthermore, and then you see here it also gets these points then correct in the end, and the weights will not change so much anymore. And as you can see, the ensemble, when you aggregate everything together, is doing then the right job. So these are correctly blue classified, this is also blue classified, and this is red classified in the end. The posterior is red there for these points. And doing this further and further, you will see that there's not much change. So here you can see also the training error reaches 0 in the end, and you can then do this for some iterations more to get then nicer boundaries in the end. And convergent means here that you, at some point, you have to decide, okay, now it's enough. So maybe again with a validation set, you figure out, okay, after 10 iterations, it's maybe good. So some properties of the AdaBoost approach is that we can, in the end, use arbitrary weak learners. So most prominent are decision trees in the end, because there it's easy to tweak them, that they are deeper or not so deep and so on. So you can make you can basically make the decision trees as strong as you want in the end, which is maybe a more difficult task when you just have the logistic regression, because logistic regression is always doing the same thing. But with decision trees, you basically can steer somehow the complexity of decision trees by using deeper or smaller decision trees. The interesting thing is that now we just use the decision stumps. So that means we had only one split node, which is a very weak classifier in the end. But as you saw, by combining all these weak classifiers together, we still get a strong model out in the end. And the only assumption is that it should do better than random guess. So when you see implementations, something like an sklearn or something like this, then you will find maybe a condition that checks if the error rate gets below random guess, then it just stops. Because then it would basically decrease the performance again when it uses the worse than random guess predictions in the end. But this is the only assumption that it's made there. And one other cool property of the AdaBoost approach is that it has the ability to use a cascaded approach. So that means we not always have to evaluate all weak learners all the time, because at some point we will figure out that the prediction that we already made cannot be changed anymore. So it's maybe getting so positive that even if we would now look at the other weak classifiers, because they are just weighted by alpha m, and they will only do -1 or 1, and therefore we can just stop evaluating the weak learners when we found out, okay, this part is already so positive or so negative that it cannot be possibly changed by the other weak learners anymore. So therefore we can just stop there. And this is a very powerful approach, because for some parts of the feature space, we are just maybe fine with having one weak learner that just says very confidently, okay, this turns not out to be a good thing, or maybe a few weak learners, so to say. And as you saw, what is also a nice property of the AdaBoost approach is that it generally converges very fast. So, but we have made now a step in the right direction, so to say. We now have a powerful approach to basically learn an ensemble that also improves over time. But we made also a step backward, because we are now again with this functional view of the classification models. And as I said, probabilities or confidence values are maybe something that we want to have, especially in robotics. And therefore, yeah, just using AdaBoost will not be maybe something that we want to have in the end. So And the question is, can we maybe do something to make it more general? And the thing is with AdaBoost, is a specific kind of boosting algorithm. So the underlying assumption was that we have the so-called exponential loss. So here the exponential loss is formulated like this. So, and when the weak learner or the ensemble puts out -1 or 1, so when they agree, the loss will be 0. If they are not agreeing, then the loss will change and it will be larger. So this is the thing that was the underlying assumption there. So therefore, this term is also appearing in the weighting term, so to say. This was the thing that was behind. So depending on the loss, we can now derive very different boosting algorithms. There were also some works that then investigated what happens if we are using just the logistic regression rule for the weak learning and so on and so on. So, so that means the AdaBoost optimizes for the example to minimize the exponential loss on the training data in the end. But can we maybe use also the functional optimization that we have? So we really optimize this h of x in the end. So we not had specific access to the parameters of the model in the end as we assumed before. So when we optimized the logistic regression with the gradient descent, but we optimized here in the end the function what we get out in the end. So because each decision tree could do whatever it want, but by going in the right direction, we could just change it in the right way, so the ensemble in the end. So can we use this functional optimization idea also for other losses? And of course, when I ask this question, then of course the answer is yes, of course. And this comes to the idea of gradient boosting. So as I said, over time people investigated different models and found out, yeah, we can also use some similar ideas like AdaBoost for other loss functions. But the gradient boosting idea was then, yeah, the thing that people found out, okay, this is really the unifying thing. So gradient boosting can be used for all different losses. So gradient boosters optimizes exactly now this ensemble in the function space. And the general idea is that it's a functional optimization, that it's similar to gradient descent. So that means we have a representation of h of x, and in each step we do a step in the right direction such that h of x is better from the loss perspective. Again, we can use the weak learners, but now the weak learners are regression models, which sounds a little bit strange because in the end we want to do classification, for instance. But I will show you how this works. So, and the regression models will approximate basically the functional gradient in the end. And as I said, in gradient boosting improves h of x, so the ensemble, without knowing its functional shape in the end. So it doesn't assume something about the weak learner and specifically optimize the parameters for the weak learner, but use it what the weak learners basically give out in the end. And by using the results that it gets out, it then optimizes the function. And to get some intuition about what is gradient boosting actually doing, here's some, I try to explain it here for the regression case. So let's say we have now our training examples like this here, and we have now our ensemble that is predicting maybe this line. And what gradient boosting does internally is basically learn a representation of the gradient function, which not is analytically derived, but just learned. So that means we first determine the residuals. So from the function that we currently have to the training examples. So in this case, in this regression case, these are just the square distances to the training points, and then we use this as our approximation basically of the gradient. So where we have to, in which direction we have to change basically this red functions such that it does a better job in the end. And we have now point estimates, and what gradient boosting does internally is to approximated with some weak learner. So that means we have a regression model in the end that tells us for every x how the gradient will look there. So it's just an approximation of basically the function such that we can change the function now such that it does a better job in the end. So, and then we can use this gradient function to then update our function in the end that we want to approximate. And this is basically the idea. So at each stage, we are determining the residuals or pseudo-residuals in case the negative gradients in respect to the loss. And then we approximate a weak learner that somehow approximates this. And then we use this to update our function in the end. And the general gradient boosting algorithm proposed by Friedman in 2001, where he calls it gradient boosting machines, is working as follows. So we initialize our first model by just using determining a constant that minimizes the loss. So here this L is basically the loss term. So it can be an arbitrary loss, so the L2 loss, or the cross entropy loss for the classification, but we come to this in a bit. So, and as again, we do the stage-wise optimization. Then comes the part with the difference between what we currently have and what we want. And this is basically the gradient now in respect to the loss over the h of xi. So, and we are just using the last ensemble that we have, and we determine this for all the training points. So, and these are basically the residuals, but the residuals, not the difference maybe in the points, but the residuals in respect to the loss. So how do we, or in which direction should we go to improve the loss for the specific points? This is captured in this line here. Then we use our regression model. So the weak learner h of m is now a regression model that optimizes this. So it just wants to optimize such that the h of xi is near to the pseudo-residuals here. So, and this is basically then the approximation of the gradient of the ensemble at that point in time. And then one step that is done by Friedman in the work is that we find basically a step alpha which improves the loss in this case. So we have our old ensemble part, and by adding then the h of m, we're going in the right direction. But we also want to determine the step that improves this as much as possible. And so we want to minimize the loss, and we want to find the alpha that achieves this. And then we update our ensemble by having the old part of the ensemble, and then putting our h of m, our weak learner, so our regression model on top of this, and then we get a new ensemble. And here the scale of the update, so this alpha m, is selected for each video learner optimally. And this is, looks a little bit complicated, but it's in the end not so complicated at all when you see now how you can implement it for the classification case. Here a little simplification, so this is something that you can do in the end. Here we saw that we initialized this with a constant, but in the end it doesn't matter so much. We can also just initialize the whole ensemble with 0. And then instead of using a specific step length, we can also then just use the idea from gradient descent that we're just doing a small step. So this nu is the shrinkage, or learning rate in this case, and this is then the whole algorithm. So the only part that you have to do basically is to determine the gradient in respect to the loss for the last part of the ensemble, then fit some regression model, and then do the update of the ensembles. And one specific case, again, decision trees are very popular because they are simple. It's the so-called gradient tree boosting. So And for the regression approach, we have now a decision tree for regression problems. And here the difference to the classification regression tree is that the regression tree is basically just returning real values. So therefore also the name for this specific kind of gradient boosting is then the gradient boosted trees or gradient tree boosting. And I will use now the term gradient tree boosting. And for the regression part, we just have the same algorithm in the end as with learning decision trees. So you recursively build the tree, but now the targets are basically not classification labels in the end, but real values. So, and with this, of course, we have to return in the leaves not a class distribution anymore, but yeah, here we return the functional value here, so the yi, so some real value in the end. And the training objective is, of course, we want to minimize the squared error, so this is the L2 loss in the end. And the splits functions are still the same as before. We're just splitting the feature space according to some dimension on the features, and we use this tau to go left and right. So this is exactly the same as for the classification trees. But of course, we have now to change a little bit to make the regression work in the end. And as I said, building the tree is just the same as before. We are passing in the data, and then we are going through this tree and then split the samples up in different parts. And then we have to determine the quality basically of the split. But first, what do we do when we reach the leaf? Because we now don't have classes, so we don't return the probability distribution in the end, but we are just returning the mean over all examples. So this is the mean over all examples that reach this leaf. This is just the part that is returned by the regression tree. And to determine the quality of the split, we cannot use the information gain anymore, but we have to do here a little bit something different. So we are just assuming that we would split there and then would stop splitting. So that means we would produce two leaves. And therefore, we are just checking here how well does such a leaf, or how well would a leaf predict basically the values that we have there. So therefore, we do this for the left part. So this is the L2 loss for the squared error for the left part and the squared error for the right part. And we select the split such that the average is a good estimate of this in the end. And this is the only thing that you have to account for. It's not so complicated. So you will be able to implement this. So and this is the only thing that you have to change. The rest of the algorithm stays the same. So you're doing the splitting, you're passing on the data, you do the recursive update of the decision tree by adding children or something like this, and then you're done. And for gradient tree boosting now for the multi-class classification, we are now just doing one thing. We are just including here in the softmax. So this is again like in the softmax regression, we have the softmax over outputs of functions. And here in this case, we are not specifically saying that the function has a specific shape, something like in a softmax regression, we just assume that there is a linear dependency between the axis. So we had here theta transpose time x, but that's the same. So we're just replacing this by individual ensembles that we learn for each class, basically. And as you remember, when you write it down, so for one specific k, then this is just the exponential over the cased ensemble divided by the sum over all of the exponentials. So and this ensures that the entries and the probability distributions are between 0 and 1 and sum up to 1. So nothing too surprising here. So the only thing is here basically you learn now not only one ensemble, but you learn k ensembles. And when we now use the negative log likelihood on the softmax, so you remember this from the classification lecture, you just put a minus log in front of this, then you will get out basically this term. And as I said in the tutorial, this term is also called cross-entropy loss. So nothing so surprising. So and this is the thing that we now use in the gradient tree boosting. So this is our loss function. And as you remember, the first step of the gradient tree boosting algorithm was to determine the gradient of this loss function in respect to the current ensemble. And this just is then this term here. In the softmax regression, this was P of y equals k given x. So this is just here now the output of our ensemble method. And from this, we are subtracting the indicator function. And as similar to the softmax regression, we now determine how we should change basically this h of k, this case h function, such that it goes in the right direction in respect to the loss. This is then the thing that we need to decrease basically the negative log likelihood loss in the end. And to give some example of this, I did the same exactly as with the AdaBoost algorithm. So I implemented this and just used a regression tree with a single split node. So the depth of the regression tree is basically 1. It's the same as before. And as you can see, as over time, the error is decreasing, but also the negative log likelihood. So, and as you can see, it also finds the splits in the right way and decreases the errors. It's not reaching 0 in the end. Maybe it needs more, but maybe here, maybe the regression trees with just one split is maybe not enough to get a good estimate of the gradient in the end. But still, you can see with this very simple regression model that approximates basically how to change this ensemble in the end, we get still a good result in the end. And then here you see that the negative log likelihood decreases. This is something that we want to have in the end, but I stopped this as 25 iterations in the end. And yeah, we can do this for much more iterations. Maybe we have to increase the shrinkage a little bit. I think I used here 0.1, but maybe we can do larger steps, especially in the negative log likelihood, by just using a larger nu value in the end. And the cool thing is that we, of course, can now also do it for multi-class classification results. And as you can see here, again, this is showing the posterior, and the purer the color is, so to say, the higher the probability is that the classifier would turn out in the end. And as you can see, it's doing here a good job in the end for approximating this. And the thing that you have to remember is that there are very simple models involved here. So the regression tree is only having one split, and then it decides on the split, and then it does this thing. So yeah, and yeah, you can see that it's doing the right job. And as you saw, the gradient tree boosting in the end is just 4 lines of code. So this is all that you need. You need, of course, the regression tree implementation, which is maybe a little bit more. But if you have this thing, then you can use this algorithm, and it works quite well in the end. As you can see, the negative log likelihood is decreasing. And as I said, this method, so the random forest and the gradient tree boosting, or the gradient boosting generally, are very strong off-the-shelf models. So therefore, using them to solve your problem in the end, your classification problem, is never a bad idea in the end. So gradient tree boosting is very popular, basically. And the gradient tree boosting is also the best performing model in many Kaggle challenges, because it's yeah, it's very powerful because you can train it for whatever, 1,000 times, and then you get a very strong classifier out in the end. And the thing that people thought about boosting is that it's not so overfitting in the end. So the risk of overfitting is not so large. So you can train it for very long times and you still get out a model that is performing very well on test data in the end. But of course, we have to find the right hyperparameters. In practice, yeah, you have to always set it according to the validation set. So this is telling you what are good parameters in the end. And yeah, in practice, you're using something like decision or regression trees. So decision trees in the AdaBoost algorithm, or maybe regression trees in the gradient boosting of 4 to 6, and then do several hundred of this boosting rounds. And I would say the same is maybe true for the random forest. So, but as I said, it really depends on your problem and how it works out in the end, and therefore this is something that you definitely have to figure out on the validation set. And with this, we are coming to an end. So in a short summary, so we discussed today some ensemble models, and I hopefully convinced you that it's a good idea to use such ensemble models in the end. And the very simple thing that we discussed in the beginning was the bagging. So usually you can maybe apply this both together. So you learn the different regression tree models and then just use bagging in the end to reduce the variance. So this can be applied together in the end. So, but we talked also about random forest, which is also a very powerful model to learn good classifiers in the end. And but as I said, they can also be applied to regression problems and to other problems. And we talked about the boosting algorithm. And here some tree creeped into the figure, but yeah, I will fix this later. So, and as I said, all these models, or at least the random forest and the boosting models, are something that you can just use. They are very powerful off-the-shelf models. And as I not covered really now parts of the books that I said in the beginning, so the computer vision models and inference book from Prince, or the mathematics for machine learning book. So here are some references where you can maybe read more about bagging from Leo Breiman. Yeah, the AdaBoost paper, this is this, so ignore this. So this was only a note that I want to cite this part. Here is the reference where AdaBoost was first described. Then the gradient boosting machine models, so there are also derivations in how to do maybe the step size in a more specific way, also for different problems like regression problems, but also classification problems. And all of these parts, so like bagging, boosting, and different variants of boosting, and what it also means, what you can also maybe do then with the boosting model in the end, so like feature interpretation and something like this, is also covered in the elements of statistical learning. So this is the book that I also mentioned in the tutorial last time. So, and here this is also freely available, luckily. As I said, you can look online on the PDF, but if you really like the book, then it's maybe also a good idea to just buy it and then have it in your shelf. But anyway, therefore I made a red boundary around it. So the elements of statistical learning, and as I said, for the decision forest, definitely the Kamenisi technical report is very well resourced to get more information about decision trees and decision forests, and what you can do with decision forests, and what different applications are possible also with decision forests. So therefore, these both I would highly recommend to have a look at. And yeah, with this, thank you for your attention, and see you next week.